The North has drawn men from many lands. Man's civilization has spread generally to the northward, toward the center of a circle, the Arctic. This region may well become the aerial crossroads of the world. It may also assume new importance in the defense and future economy of the nation, for it is here, in northern Alaska, that there are indications of new sources of petroleum in North America. In an area of 37,000 square miles, known as Naval Petroleum Reserve Number 4, the Navy's Seabees first began the oil exploration in 1944, using modern tools and equipment to overcome severe Arctic conditions. The work continues today under Navy supervision as commercial contractors apply the skill and experience developed by private enterprise, both at home and abroad. Alaska is large, twice the size of Texas, 1/5 the size of the United States. Yet, its population is only about 75,000. 30,000 of the people are Eskimos and Indians. From south to north, there are 4 temperature regions: the coastal, subarctic, Arctic, and the polar. Our interest is in Naval Petroleum Reserve Number 4, an isolated region hemmed in to the north by the Arctic Sea and to the south by the Brooks Mountain Range, which has not been crossed by highway or railway. North of the rugged Brooks Range is the Arctic Plateau, an area of steep and rolling foothills. Still farther north and extending to the Arctic Ocean is the low, flat coastal plain, dotted with lakes, meandering streams, and swamps. Winter in northern Alaska is a period of long nights, near darkness, extreme cold, and wind-driven snow. Here, there is no direct sunlight from mid-November to late January, only 2 to 4 hours of twilight daily. The temperature averages 20 below zero during the winter, and the seasonal wind averages 10 to 15 miles an hour, creating snowdrifts elongated northeast, southwest. The temperature may fall as low as 55 below zero, and on rare occasions, the wind may reach a velocity of 100 miles an hour. The winter snow is light and not much of a hazard. As much as 8 inches of snow falls in October. During the winter, the ground is generally frozen solid to at least 900 feet, possibly deeper in some regions. Only the upper 1 to 5 feet is newly frozen. The rest, permanently frozen, is called permafrost. Bodies of water commence freezing in September, and by mid-February, the ice is 48 to 55 inches thick, reaching its maximum thickness in late May. Winter breaks in late May or early June. The rivers and lakes are usually ice-free by mid-June. The ocean ice off Point Barrow begins to break up during July. The easterly wind may be expected to blow the ice off the Barrow Beach about the 1st of August. A sudden reversal of the wind and currents may blow the ice back at any time. The ground gradually thaws from 1 to 2 feet deep, making the surface a sea of muck, dotted with lakes and ponds of varying sizes. The small amount of moisture lost through evaporation seems to be replenished by the rainfall, which never exceeds 2 inches during any summer month. Fog moving over the coast, lake, and river areas during July and August causes periods of poor visibility. During the few months of summer, the temperature averages 40 degrees Fahrenheit, occasionally getting as warm as 78. Summer in northern Alaska proves that the land is not barren of vegetation. There are more than 700 kinds of flowering plants on the coastal plain, as well as numerous lichen and mosses. Inland, among the steep foothills, there is similar vegetation, as well as elders, willow, and berry bushes. The willow buds and berries are edible. Reindeer moss is 8 to 10% digestible and can be eaten in an emergency. The vegetation, while generally not suitable for man's food, supports a considerable animal life, which furnishes food and clothing for man. Large herds of caribou and reindeer roam the slope. There are many foxes, weasels, lemming, and squirrels. grizzly bears, wolves, and wolverines are found in the forests of the subarctic. There are many ducks, geese, ptarmigans, owls, and ravens. Fish are found in the rivers and lakes. At sea, there are fish, seal, and chiefly to the westward, walrus, as well as polar bears. A few insects, notably deer flies, gnats, and mosquitoes, are found inland. Mosquitoes breed in ponds in great numbers, and while not disease-bearing, are troublesome. Faced with these general conditions, the native Eskimo has made satisfactory adjustments in terms of his necessary activities. In summer, a light canvas or skin tent is excellent temporary shelter, and in winter, snow houses furnish temporary shelter while hunting or fishing. A wooden shack, originally made of the fairly abundant driftwood, provides permanent shelter from wind and cold. Today, the Eskimos are building well-insulated frame houses. Outdoors in cold weather, the Eskimo protects his body with loose-fitting fur and skin clothing. He wears reindeer or polar bear pants with the fur side out. A loose-fitting hooded coat or parka of reindeer or caribou, fur side out, protects the upper body and extends to the knees. The sleeves are made so that the arms may be withdrawn and warmed against the body. The outer ruff of the hood is wool. The inner ruff, preferably of wolverine. Native footwear called mucklucks with caribou foreleg uppers and reindeer soles provide good protection for his feet. For walking over salt ice, he wears a muckluck made with a tough seal hide or ugrug sole. Eskimo winter clothing, if properly cared for, is suitable for his activities. The Eskimo has no trouble with perspiration collecting inside his clothing. The thickness of his clothing is readily adjustable to the season. He can add to its insulating value by putting on additional layers of parka and trousers, an important feature because cold creates a high wind chill effect which tends to drive away bodily heat faster than it is produced. Therefore, the Eskimo's style of clothing provides protection against wind chill, as well as offering considerable freedom of movement. Summer clothing is made from light skins or from cloth secured from the States. Watertight mucklucks with a lightweight sealskin upper and ugrug sole are worn during the summer months. Because the Eskimo's clothing conserves bodily heat, and because his cold weather activities are limited, his intake of food is not noteworthy. He eats what he can secure by hunting and fishing. Arctic birds, fish, and mammals make up his diet. These foods, high in protein and calories, are excellent heat and strength-producing agents. Although not particularly provident, tending to collect food when he needs it, and tending to feast when he has it, any excess food is stored on racks or in cellars dug into the permanently frozen ground. As hunting is the Eskimo's sole occupation, he has developed means of getting to and from his hunting and fishing grounds. The dog team and sled serves well in bringing home the kill made inland, or for hauling heavy loads over the ice. Small skin boats, kayaks, are used for sea hunting and fishing, and larger skin boats, umiaks, for trips to the sea. The Eskimo is adept at finding his way in the area with which he is familiar. He knows his own area just as anyone knows familiar surroundings. A slight feature of the terrain, meaningless to the newcomer, and the manner in which the snow forms in drifts are to him what a tree or a lamppost is to people in the States. On the whole, the Eskimo has met conditions in the Arctic by adjusting himself and his activities to these conditions in common-sense ways. Whether men of the States go to Alaska for exploration, for construction, or for military reasons, they must follow the Eskimo's lead and work with, not against, Arctic conditions. Men working in Pet 4 have evolved clothing that is suitable for the weather and the seasons and the work of Pet 4, where permanent shelter is available at will. The more or less standard summer clothing starts with underwear and socks chosen by the individual. Over this basic layer, he wears a woolen shirt and utility or chino cotton trousers. Heeled shoes, a utility jacket and cap, and leather mittens with liners complete the summer outfit. If he is to be in a muddy area, he may wear Arctics over the field shoes, or shoe packs may be substituted for shoes and Arctics. A rain parka and rain trousers are worn over the summer clothing in rainy weather. Shoe packs protect his feet. Cold weather clothing has a basic layer of two-piece heavy underwear. Cushion-soled woolen socks are placed next to the skin, covered by one or more pairs of heavy woolen ski socks. Next, a woolen shirt and the kersey-lined trousers. Then, a wool sweater, jacket, and utility trousers. Felt shoes with one or two felt inner liners cover the feet. A mechanic's parka protects the upper body and head. Two-layer Arctic mittens are worn over the leather mittens and liners. For use on the trail or in extreme cold, native fur trousers and one or two native fur parkas are placed over the other clothing. All worn Eskimo fashion. Native fur mittens replace the navy mitten combination. Native fur mucklucks replace the felt shoes. Such, in general, is the clothing worn by the men working in the Petroleum Reserve. Present clothing is satisfactory where permanent shelter is available. It provides warmth and comfort. It meets occupational needs and permits present work to go on throughout the year. It would not, however, be satisfactory for military field operations. For such use, thorough study should be made. The clothing of the Eskimo should be copied with respect to styling, freedom of movement, the character of the fiber used, and adjustability in thickness. Clothing should be designed to meet combat and military occupational requirements. Men from the States can hardly follow Eskimo practices in eating. Since large groups of men cannot live off the country and would probably find native food unpalatable at first, food requirements must be carefully planned. Up to 5,500 calories of food per day are required for each man. The food served includes abundant proteins, meat and eggs, fish, sugar, and fatty foods. A vitamin supplement is included. Tractor trains move heavy supplies in Pet 4 after the ice on bodies of water is thick enough to support the load. Tracked vehicles, such as the Weasel or LVT, provide faster overland transportation in winter. Small ski planes make rapid, light transportation possible. In the summer, transportation inland is limited to small boats on the rivers, float planes, and small wheel planes for which a river gravel bar can serve as an airstrip. Ocean transport is possible only for a 4 to 8 week period during the summer, providing the winds are favorable. Only during this period can heavy supplies in quantity be delivered to northern Alaska. However, the airplane is the only round-the-year means of transportation with the outside world. Construction in the Arctic requires an understanding of the ground, not only of the active layer which freezes and thaws annually, but also of the permanently frozen ground beneath. Almost anyone can get along in the Arctic if properly indoctrinated. However, practical men of average intelligence do best in the Arctic. Training should be twofold. First, providing a broad knowledge of Arctic conditions and how to get along under such conditions. And second, conducting operations under Arctic conditions for extensive periods with careful supervision and discipline. Knowledge can be gained secondhand. Wisdom and capability come only through experience. The Arctic presents no insurmountable obstacles. With careful planning, complex operations can be accomplished on time and efficiently. The basic objective of operations in Naval Petroleum Reserve Number 4 has been to explore for oil. All other projects have been secondary. The PET 4 Operating Committee determines the methods to be used, as well as the extent and locations of the exploration. Early in the exploration, the committee had a possible pipeline route surveyed, for any oil found would be useless without an efficient way of getting it out of the reserve. Wide areas in PET 4 have been covered by various geological and geophysical methods. Several wells have been drilled. The objective is oil in commercial quantities. The first step is to find structures favorable to the accumulation of oil. If we were to remove a part of the Earth's surface, we might find an elongated under-earth structure called a closed anticline. If we look at this in cross-section, we see that the strata of rock are upfolded or arched and dip away from the crest in all directions. Such a structure is favorable to the accumulation of oil. In addition, there must be a porous and permeable layer which is overlaid by an impervious layer of caprock. It is this porous and permeable layer that may contain oil. Only one way exists to find out. That is to drill into the structure. In this film, we shall consider the methods of exploring for oil used in PET 4. The basic geological method of exploring for oil is to study the outcrops which are found frequently along rivers and streams in PET 4. A single outcrop gives information on the character of any rock layer, its thickness, the angle between the layer and a horizontal plane, the direction of the dip, and the porosity and permeability of the rock, as we see here, greatly magnified. Several outcrops may permit the geologist to determine this same information for several layers of rock, until with many layers, he has what is called the stratigraphic column of the area, a picture of the entire sequence. A study of additional outcrops gives a picture of closed anticlines in the area. Let us now see how geologists working in PET 4 have used the methods of studying outcrops to determine the character of the rocks and to locate closed anticlines. Sometimes the outcrops are so apparent that visual inspection from an airplane gives a good indication of an area to study in detail. As no dependable maps for the area were available, the Air Force, Navy, and U.S. Geological Survey have cooperated in developing maps by aerial photography for use in exploration studies. Aerial photography is also an excellent basis for selecting areas for outcrop study. The Operating Committee considers the recommendations of the U.S. Geological Survey as to the areas to be studied, the number of parties needed, and the food and gasoline caches necessary to do the job. Food, gas, and oil are cached for each geological party. Bush planes carry the geological parties to their initial stations. At the field station, they set up their balloon silk sleeping tents and the cook's tent. A typical party has 4 men, 2 geologists, a field assistant, and a cook. They break out their collapsible canvas boats and get them in shape for use. Sectional wooden boats have proved less satisfactory. When the work is started, the surveyor sets up his plane table and alidade to shoot in the location of all stations. All outcrops around the initial station are visited. The attitude of the strata are noted. The weathered surface of a rock is studied as well as a freshly broken surface. Samples of rock as well as macrofossil evidence, such as clam shells, are collected for later analysis in the laboratory. The surveyor may be called upon to measure the thickness of the rock layers. In a bed of coal, an uncontaminated sample is taken for laboratory study. Camp is moved when trips to and from outcrops take too much time. Moving for a river party is usually a matter of floating down the river. In places, the rivers contain many large boulders and many rapids. Portaging may be necessary. Or the boats may be lined through by having one man wade alongside the boat in water of 35 to 40 degrees Fahrenheit, while another man helps with a line on the shore. Sometimes the boats must be dragged over bars where the river is wide and shallow. At the new station, the same studying of outcrops and taking of samples continues. Only now, an attempt must be made to correlate the new findings with previous ones. The study of outcrops continues throughout the summer, and supplies from the outside are brought in by plane. Food is backpacked from cache to camp, and daily communication is maintained by portable radio to Umiat, perhaps 250 miles away. Weasel parties are very similar to the river parties, except for the mode of transportation. They leave Umiat after the snow is off the ground. A weasel party has the same staff as a river party, except for the addition of a weasel mechanic. Camp is made, and the geologist goes into the field, measures the dip and strike, and maps the geology of the area. At the end of the field season, parties are returned to base camp by weasel, or float down the river to Umiat. Some are brought back by plane. In the laboratory, the rock samples are carefully studied for porosity, permeability, and the micro and macro fossils, all matters of importance in oil exploration. Back in Washington, the geologists fill in geologic maps, prepare cross-sections, work out stratigraphic columns, and write their reports. With the data on underground structures now assembled, the aerial photographs are restudied, and attempts are made to fill in the structures in interstream areas where there were few outcrops. Outcrop studies have covered considerable areas in PET 4. Core drilling is another method used by geologists to find out what lies beneath the surface of the earth. Sometimes there are no outcrops or too few outcrops to indicate the character of the rock beneath the overburden. In such instances, core drilling gives additional geological information. The procedure in core drilling is generally similar to deep well rotary drilling. A square or octagonal pipe called a kelly is suspended from a swivel. The kelly extends through a rotary drive bushing. Attached to the lower end of the kelly are joints of drill pipe. To the bottom joint of pipe is attached a core barrel and bit. A nearby mud pit furnishes drilling fluid. A hose attached to a pump connects mud pit and kelly. The drilling fluid is pumped through the hose into the Kelly and down through the drill pipe. At the bottom of the hole, it picks up the drill cuttings and carries them up into the mud pit where the cuttings settle to the bottom of the pit. The core hole may be drilled from 300 to 1,400 feet deep, depending on the rig and the information required. Inside the barrel is the core sample, as we see in this cross-section. The hole may be cored at intervals or cored continuously. Also, ditch samples may be taken when required from the discharge line entering the mud pit. The samples from a single hole indicate the stratigraphic column at that locality for the depth drilled. Such core and ditch samples may be used to assist in locating favorable structure as well as stratigraphy. In Pet 4, core drilling has been used primarily to determine the stratigraphic column. Let us now see how the actual process of core drilling takes place in Pet 4. The job starts in Barrow Base Camp with the usual construction and thorough preparation that must mark all operations in northern Alaska. From January to March, the core drilling equipment is moved out from the base camp. Personnel will go out later by air. On location, camp is set up. The party will eat and sleep and work in these wanigans. The drill rig wanigan and the adjacent mud pit wanigan are the center of core drilling work. This equipment is so constructed that no rigging up is required in the field. The derrick is already up. The portable mud pits are ready. In preparing to drill, the men merely have to put the sleds in position and make a few electrical and flow pipe connections. Inside the rig house is the drilling equipment. Here is the Kelly, which acts as a drive shaft, the swivel which holds the Kelly, and the hose which carries mud into the drill pipe. Here, too, is the drive bushing which rotates the Kelly, the drill pipe, and the bit. In the adjacent mud pit wanigan is the portable mud pit. It contains a mixture of water and pulverized clay particles. Sometimes additives are introduced to change the weight or viscosity of the mud. It is tested 2 or 3 times a day for density, viscosity, and temperature. It is kept warm so that it does not freeze while passing through the permafrost. When the predetermined drilling depth has been reached, the pipe is removed joint by joint. Attached to the last joint is the core barrel and bit. The bit is removed. Then, piece by piece, the core samples are removed, washed, inspected, and placed in a core tray ready for shipment to the laboratory in Fairbanks. In Fairbanks, the samples are carefully analyzed. The information secured is carefully correlated with information secured from other core tests and from study of outcrops. Back in 1944, the Navy Seabees began core holing on the reserve. It continues today, usually during the summer, but may be carried on the year round. To date, 18 core holes have been drilled in Pet 4. One geophysical approach to finding underground structures favorable to oil is magnetometer surveying. The theory is relatively simple. Basement rock underlying sedimentary rock has limited magnetic properties. Thus, variations in the magnetic intensity as measured above the surface may give a tentative picture of the features of the basement. From this, inferences may be drawn as to the probable geologic conditions warranting further exploration by other methods. In Pet 4, aerial magnetometer surveying has been completed over wide areas. A PBY 5A carries the magnetometer aloft. The The results of these magnetometer surveys indicate specific areas for further geological and geophysical exploration. Another geophysical approach to underground structures is gravity meter surveying. The theory of gravity meter surveying can be outlined quickly. The closer the basement is to a fixed altitude, the greater the gravitational attraction of the basement. If the amount of gravitational attraction is measured, a tentative picture of the underground massed structure can be made. From this, inferences can be drawn as to the probable geologic conditions and the nature of any underground structures. Gravity meter work in PET 4 takes place from March to September. The meter is carried from station to station by air. During winter, the plane lands on a frozen river or other likely spot near the survey station. The meter tripod is placed and leveled. The gravity meter is then placed on the tripod. The location is marked by a flag for future reference. The meter has an electrical connection to the plane. This permits the meter to be kept at a constant temperature, a necessity if readings are to be accurate. An altimeter reading is taken so that the gravity meter readings can later be corrected for altitude variations. The gravity meter is then carefully adjusted and read, and all data entered in the field data book. The gear is returned to the plane, which takes off for the next station, usually about 5 miles away. Back at base camp, the data from several stations are plotted on base maps after appropriate corrections. The base map is then used in PET 4 to select areas for investigation by other methods, especially the seismograph. A third type of geophysical exploration occurs in PET 4. It is seismograph surveying by the reflection method. Let us look at the theory involved. A charge exploded beneath the surface sets up seismic waves, which are transmitted by particles of matter. These waves increase in speed when they strike a stratum of increased density. At such points, an energy wave is reflected to the surface and recorded on tape. A part of the wave continues to a lower stratum, where again reflections to the surface occur. If these reflected waves are carefully recorded, timed, and interpreted, a picture of the attitude and depth of the reflecting beds is secured. From several such records of carefully located explosions, one has data from which the subsurface structure may be interpreted. After camp has been set up and equipment serviced, a hole is drilled with the same equipment used for core drilling. These holes are usually from 50 to 100 feet deep. While the shot hole is being drilled, the recording weasel is moved to its position. Connected to this weasel is the cable, which is reeled out along a line already marked by the surveyors. At marked points along the line, holes are dug. The geophones are placed against the ground. Several geophones, 120 feet apart, are connected to the cable. These geophones will pick up the reflected seismic waves and change the wave into an electrical signal which travels along the cable to the recording weasel. Back at the completed shot hole, dynamite is lowered and the hole tamped by filling with water. As the hole is shot, nearby in the recording weasel, a record is made. The electrical signals from the geophones are stepped up in the amplifier, transmitted to galvanometers, and recorded by the camera. When the shooting is completed, the geophones are detached and the cable reeled in. Several such holes may be shot in one day. At the end of each day, the records are carefully studied by the seismologist. He picks the reflections and marks the time of each reflection in seconds after the shot. He also inserts exact times on the time lines. These data are then used to compute the depth and dip of the reflecting beds. From such information, cross-sections are prepared. With sufficient data from many shot holes, structure contour maps of the reflecting strata are made up. This geophysical method is widely used in PET 4, particularly in the Arctic plain, where there are few outcrops. Seismograph surveying continues until about the middle of September. The various geological and geophysical methods so far considered in this film give indications of underground structures favorable to the bearing of oil. To find out if there is oil in the structure, a well must be drilled. 3 deep test wells have been drilled in PET 4. In addition, shallow oil tests have been drilled in connection with core testing. Test well drilling in PET 4 is not very different from drilling elsewhere, except for special problems due to terrain, construction, and the extreme cold. At the well site, supplies and equipment are unloaded. With the start of construction, problems peculiar to PET 4 begin to occur. For winter drilling, the derrick must be completely enclosed with insulating canvas to protect the men and the gear from wind and cold. Even the crown block is enclosed. The rig house connected to the enclosed derrick houses the mud pit and pumps. Inside the rig house, the drilling fluid is heated by steam coils in the mud pit, so that the mud flows readily from the hole deep in the permanently frozen ground. Space heaters in the rig house help keep the drilling fluid warm during cold weather. Heat escaping through the opening to the enclosed derrick keeps the temperature adequate for the workman. The mechanics of drilling in the Arctic are the same as those used anywhere else in the world. A bit is screwed into the drill collar. The drill pipe is screwed together in 80-foot stands and run into the hole. The driller controls the weight on the bit by means of a weight indicator. When the bit becomes dull, the drill pipe is pulled, racked up in 80-foot stands, and the bit removed. The petroleum engineer tests the mud for weight, viscosity, and temperature. When cores are taken, the geologist assembles them in trays, inspects and describes them, and examines them under a microscope. Throughout the drilling, the driller keeps an eye on the gas indicator for possible signs of gas in the drilling fluid. The driller is always ready to operate the remote controls which close the blowout preventer and thus keep mud and tools from being blown from the hole by high-pressure gas and oil. Every 1,000 feet, it is customary in PET 4 for the petroleum engineer to run an electric log as a check on the rock strata penetrated, their content, and their porosity and permeability. The tape record is made by hand recording equipment. Because of the relative lack of knowledge of the PET 4 area, the electric log has not supplanted coring. When the hole has reached its maximum depth, the petroleum engineer makes a temperature survey of the hole. This helps him to determine the thickness of the permafrost. A thermometer is lowered into the hole. Drilling continues the year round, regardless of Arctic conditions of climate and terrain. Present plans call for continuing the exploration for oil in PET 4 through 1953. The work to be done includes 4 seasons of surface geological exploration, 2 seasons of core drilling, 1 season of airborne gravity meter surveying, 4 seasons of seismograph surveying, and 4 years of test drilling, 1 deep test, 1 medium test, and 1 shallow test well each year. The exact location of these wells will be determined from geological and geophysical findings. In addition, the necessary supporting operations are planned. Thus, the Navy continues its search for oil in the Arctic. In this age of oil-powered machines, so important in peace and war, PET 4 holds great promise for making a significant contribution to our national defense and economy.